In this video, we're going to derive the sum identity for the sine function. So I've included the sum and difference identities for sine for you to look at. I'm not going to read them. You can always pause the video if you need to read them carefully. Just like the sum and difference identities for cosine, we want to show where they come from so that we don't think they're magical. I'm going to derive the sine, the sum identity for the sine function, and then I'm going to leave deriving the difference identity for the sine function as an exercise for the homework, but the method or technique for doing the derivation will be nearly identical to that I do for the sum identity for the sine. So the way that we do this is we're going to let an angle theta be the sum of two angles alpha plus beta. And what we want to know is, what is a way to describe the sine of alpha plus beta in an identity format that will be useful to us down the road? And the tool that we use is actually an identity that we've already come up with. We've already did the cofunction identities. It was something that we did early on in the video sequence where we demonstrated that the sine of an angle theta was equal to the cosine of 90 degrees minus the angle theta. And we did that by establishing a right triangle. And we labeled one of the angles theta, which then forced the remaining angle to be 90 degrees minus theta, because the sum of the angles of a triangle had to add up to 90 degrees. And what we recognized in that particular video was that if this is a radius or a hypotenuse, and we define the cosine of theta to be, or the sine of theta to be opposite over hypotenuse, that for the side opposite, for the angle 90 degrees minus theta, that side will be adjacent 90 degrees minus theta, and we'll get adjacent over hypotenuse. So we get the same side ratio by doing the sine of theta or cosine of 90 degrees minus theta. So we step over, and what we do is rewrite the sine function using theta to make our life a little bit simpler. So I'm going to say, hey, sine of theta is the same as sine of alpha plus beta, because theta is alpha plus beta. And then what we do is apply the cofunction identity to rewrite the sine of theta as 90 degrees minus theta. And we do this because we already have a difference identity for the cosine function that we can manipulate and use to see if we can get something useful out of it. So we get cosine of 90 degrees minus theta, but theta is really alpha plus beta. So I can make a substitution there. And then I can distribute the minus sign and regroup things. So I can go cosine of 90 degrees minus alpha minus beta by distributing the minus sign into the parentheses. And then I can use grouping to group and say, hey, I'm going to do the 90 degrees minus alpha first before I subtract the beta. And if I do this, I have a form here where here is one angle minus another, and I know how to deal with that. The difference identity for cosine says that if I have the difference between two angles, I take the cosine of the first angle times the cosine of the second. And if it's a minus, I'm going to get a plus right here, and I'm going to take the sine of the first angle times the sine of the second. And it happens to be that our first angle is a 90 degrees minus an alpha. The second angle is a beta. Then the first angle is a 90 degrees minus an alpha. And the second angle is a beta. And then I look at this and I realize that, ooh, I have a cofunction identity sitting here. Cosine of 90 degrees minus some angle is just equal to the sine of the angle that's being subtracted from the 90 degrees. So I can rewrite this using the cofunction identity as the cosine of alpha. Sorry, as the sine of alpha. The cosine of 90 minus an angle like alpha is equal to the sine of that angle. So it's going to be the sine of alpha times the cosine of beta, and then I have my plus, and then I get the sine of 90 degrees minus alpha, which right here I see if I have the sine of 90 degrees minus an angle, it's just the cosine of that angle. So I can replace the sine of 90 degrees minus alpha with the cosine of alpha, and the sine of beta stays the way it is. And then we recognize that, hey, this came from manipulating the sine of alpha plus beta using other identities, which establishes the result that we see up here in the box. And you get to do this one as an exercise.